Okay, so previous slide I just introduced what's the reason we don't lack the wake flow, because the wake flow will induce the drag force for our object. So the key knowledge is if there is no flow separations, there is no wake flow. So we wondering to know the reason why the flow will to be the separate from just a flow far away from the object. So we go back to see the velocity gradient profile, okay? And you can see the top is the condition for the pressure gradients. As I mentioned before, the pressure gradient is less than 0. That indicates the particle flow is the accelerate conditions. But if you see the pressure gradient larger than 0, that indicates that the fluid particle is decelerate. Okay, so in that case, if we see the fluid particle accelerate and you see the velocity profile for the bottom point in here, the velocity gradient along these directions, as you see the slope is very very flat. That indicates the velocity gradient is much larger than 0. Okay, and if you see when the pressure gradient is equal to the 0 in here, and the velocity gradient at the bottom point will to be the gradient much larger, and until the velocity gradient equal to the 0, and then you can see the flow velocity at the bottom here. The slope is the vertical line. After these conditions, we will see at the first flow. We will see that at the first flow, and we call that the region will have the separation flow, and this is the point we will observe the flow start to separate. We will observe the flow starts to separate at this point. So this is the condition when the flow will start to separate of the object. And the right hand side here, this is the condition we will observe the separation flow in that region. Okay, so we put the velocity profile into the object. So you will see the reason why I say that the conditions, and this is the point, the flows start to separate. After the flow start to separate, and then the region we will observe some adverse flow velocities, and we will have some recurve, the circular flow at the front, at the back of the object. And that's a region we say that this is a wake flow regions, and this is a wake flow regions we don't lack because there is some the pressure drag force in this direction. Okay, we will have the sorry, I saw it wrong. It's a right hand side is the drag force we don't want. This is a drag force we don't want. So the main ideas for this slide, I wanted to emphasize, we need to identify the velocity profile, and we can see where is the separation point. So it just depends on what kind of the profile velocity you observe, and then you can identify where is the location the flow start to separate. Okay, so if I go back to see the CP values around the object, as I mentioned, the CP coefficient can help us to describe the pressure field surrounding the object. So this is an ideal case. For this ideal case, we cannot observe any wake flow. And for the CP value, if we see the CP value is the positive, so there is a region the CP value is the positive, and there is a region the CP value is negative. So the curved line in here is the CP values curved line. If you see this is an inward curved line, it indicates the CP is the positive. If you see the outward curved line, it means the CP is negative. So how can we determine the CP value is positive or negative? It's just based on the piezometric pressure difference here. Okay, the piezometric pressure compared to the free streamline piezometric pressure is larger than or less than, and you can determine the positive pressure CP value or negative for the CP value. Okay, but this is for the ideal flow if there is no any wake flow happened. If we see, so there is no wake flow happen, so you can see on the front is the positive, and on the back also the positive. Okay, so there is no wake flow, but if we can observe there is some wake flow happen in here, and you see the CP curvature is totally different, especially the region in here. Okay, you can see the region in here. Initially, the region in here is the positive CP value, but right now we change it to the negative CP value. That indicates there is the, as I mentioned, the wake flow region is lower pressure. And if there is lower pressure regions, and we will have the drag force in these directions. Okay, so we will have the drag force, and the drag force will overcome the particle move to the left. So the drag force is in these directions. The drag force is caused by the lower pressure region in there. Okay, so there are some sentences you can read by yourself, but the idea is we don't lack the drag force caused by the lower pressure region. And the lower pressure region will increase when the wake flow increase. So if we can avoid the point in here is a separation point. If we can extend the point to be the here, and the wave flow region will become smaller. So the idea is we wondering to reduce the wake flow, we should change the point of the separation. So we should change the point of the separation. Okay, so how can we change it? The top case is there is no, it's a normal ball, and there is no hole. So you can see your separation point is in here. So the wake flow region is larger. Compare if we change the separation point in here, and you can see the wake flow region becomes smaller. So the reason why we can change the stagnation point, separation point in here, because we make the hole. We make the hole on the ball, and then the hole will induce the turbulent flow. Okay, that's the hole will have a turbulent flow effect. And as you remember, the turbulent flow, the velocity profile will equal to will close to the uniform flow. Okay, so that's the reason why we make the hole, and we have the turbulent flow effect. And the turbulent flow effect, we will have the velocity profile like the uniform flow. So we will have the separation point move to delay. Okay, but initially you know that the velocity profile would like, if like this shape, we will have the separation flow happened. So the turbulent, we make the hole on the ball, So we will involve the turbulent flow effect. And the turbulent flow effect will change the velocity profile, go back to be the uniform flow. So the separation point will happen delay compared if you don't have the turbulent flow effect. Okay, but the turbulent flow effect will involve the viscosity. That will be also not good for the engineering design. OK， 所以其实关键就是，如果我们让这个球的表面有一些 turbulent flow 产生的话，我们会让速度剖面变得比较像 uniform flow。那速度剖面如果比较像 uniform flow 的话，我们就会延迟这个分离点的发生。如果我们延迟这个分离点的发生，我在它后端的尾流的部分就会减少。Okay, so the idea we wanting to delay the separation point happens, and we will reduce the wake flow effect. If we can reduce the wake flow region, and the drag force also can be decreased. Okay, so that's the ideas when we describe the pressure field based on the CP coefficients. And this is another case. We call that this is a wind coefficient test. Okay, as you can see, when we build up the house, and this is a structure for our house, and because the CP value in here is the positive, so you will observe the high pressure in there. But when the flow just flow laterally, so the flow just flow lateral, and then there will have some the highest speed. So we will have the high velocity, and we have a low pressure. So the lower pressure, but inside the house is the higher pressure. So the inside house, the higher pressure just flow outside to the lower pressure regions. So that's why in here we call that is observe the force. And the outside region in there, we know that this is the wake flow. This is the wake flow region. Okay? So the wake flow region, we also have a lower pressure in here. We have a lower pressure. Okay? So, but right now we have some very quick exercise in here. If I know the CP value is 1, and during the typhoon period, the high wind speed is the 40 meters per second. So, how about the force acting on the house front? Okay, how about the force acting on the house front? So as I mentioned, based on this equation, I know that the CP is the 1 will equal to the piezometric pressure at the house front minus the piezometric pressure at the free string, and divided the air density multiply the velocity speed square at the location on the free string, and divided the 2. As we know, the pressure, piezometric pressure, the gauge in the free string here is equal to the 0. Okay, and we just reorganize the equation in here. So we know that the piezometric pressure at the front of the house is equal to the low air density velocity square divided the 2. And we put the answer inside, the number inside the piezometric pressure. The air of the air density is equal to the 1.2. And the velocity during the typhoon period of the wind is the 40 meters per second square, and divided the 2. So we can compute the answer is 40 square, and multiply 1.2 divided the 2 is around the 960, and the unit is the Newton per meter square. Okay, so we actually know the pressure force. The pressure force is 960 Newton per meter square. Okay, because the answer we need to find is how large the pressure force we have for meter square. Okay, so it's equal to the 960 newtons, and if you compute how large the mass you have, so you just divided the pressure force by the 1g gravity, and you know that the mass is equal to 98 kilogram force. Okay, so that's the idea. Sometimes we apply the pressure coefficient, so we understand under this condition pressure coefficient how large the pressure force we will have on our structure. Okay, so for our government, we propose the one table. It is, we call that the wind code for house. Okay, so actually for different structure front, you will have a different definition for the CP value. So this is when you build the structures, and your building should be satisfied a different code for the pressure coefficients. And it also depends on what the shape of your buildings. So the L in here is the longitude length of the buildings, and the B in here is the width of your house. It's the width of your house. So it's also related to your structure shape geometries, and you need to satisfy different pressure coefficient design. Okay, so that's the idea why I introduced the pressure coefficient, because if you go back to see the equation defined, all the parameters shown on the pressure coefficient are related to the Bernoulli equation. We just put the piezometric pressure on the top, and the bottom is the velocity pressure. And the sum of all items is equal to the Bernoulli equation, will satisfy the constant value. OK， 所以最后的这部分为什么我们特别要讲这个系数？因为这个系数是用伯努利方程的能量守恒定义去创造出一个 ratio 系数，来让你方便观察在你的结构物的外围或是任何的物体，它这里是受压的还是受阻的。哦，就是你可以了解你这些物体周遭应力场的变化，可能你不需要想太多，你只要用这个系数，你就可以知道这里是受压，或者是哪里是低压的条件，哪里可能会跑出阻力的状况，所以你就不需要再去推导，或是你只要看这个系数，你就可以去了解这个物体周遭受力的情形。哦，那最有名的就是在建筑法规里面，你的任何一个墙面所要承受的这个风阻的压力，那你是必须符合这个系数的规范，不然你这样子的设计，万一被风一吹，房子就倒了，那就跟3只小猪盖房子是一样的。OK， 所以它的概念就是，其实就是想要用伯努利，然后创造出一个法规，然后让大家去 follow 这个 CP 值，你就知道你的建筑物是在一个什么样的强度的条件下，它可以承受多少的那个外力这样子。Okay, so for this chapter, I may stop here, and then I want to introduce a little bit for the next chapter, for the chapter 5. Okay, so the chapter 5 is a topic related to the control volume approach and the continuity equations. So the major ideas for this chapter, we wondering to move the topic, the key concept, we wondering to understand how the physical property changes or exchange in our systems. And when I call that is the physical properties, include the first is the mass. So we have the mass properties exchange in our systems. Or we discuss with the momentum's physical property exchange in our systems. Or we discuss with the energies exchange in our systems. So as you can see, the following chapters, the concept almost the same, but we only change the material properties. So for the chapter 5, we wondering introduce how can we analyze the mass exchange in our systems. And then we keep the same idea, but we change the material physical property to be the momentum and the energy in the following chapters. So in the following chapter, I will teach more quickly because the same idea just apply to different physical properties. And then 3 important equations. The most important equation for the chapter 5 is the mass conservation equations, 质量守恒方程. And the chapter 6, we have the momentum conservations. So we have the 动量守恒方程. And finally is the energy conservation. Okay, so all equations are important. And chapter 4, we have 2 equations very important. It's Euler's equation and Bernoulli equation. And include the 3 equations shown here. All the equations for this semester are quite important for our fluid mechanism problem. Okay, so that's maybe I just stop here, and we will have the Kahoot quiz. Okay.